Hello everyone, and welcome to week 2. In this video, we'll go over one-sample t-tests, otherwise known as single-sample t-tests. We'll also introduce the concept of effect size and type 1 and type 2 error. We'll close by talking about the concept of power. So first of all, a quick review of t-tests. To test a hypothesis using a t-test, we need the population mean, represented by mu, and the population standard deviation, represented by sigma. But what if we don't know our population standard deviation? And this is often the case because it's much more difficult to pin down a population's variance than to pin down a population mean. And this means that we have to estimate our population variance and standard deviation. The good news is that we can base our estimate on our sample's variability. Doing so, however, requires a different type of test, which, as you might have guessed, is the t-test. A one-sample t-test asks the same question as the z-test for samples. In other words, how likely would we be to observe a sample mean this extreme if the null hypothesis were true? One-sample t-tests are more conservative than z-tests because they control for more error. I'll also note that the term conservative, as applied here, has nothing to do with political leanings. It simply means that the test is less likely to yield a significant result. Now, you may ask, why is more error involved here? And the answer is because we're missing a parameter, specifically population standard deviation, represented by sigma, and must estimate this parameter based on a statistic, sample standard deviation, S. This means that our sampling error is greater. Let's compare the formulas for a z-test versus a one-sample t-test. So you'll recall from our lecture last week that the formula for a z-test involves finding the difference between the sample mean, represented by m, and the hypothesized population mean, represented by mu. To calculate a one-sample t-test, we find the difference between the sample mean m and the hypothesized population mean mu, just like we did for the z-test. Notice that the numerators, the top of the fractions, are identical. The denominator of the z-test is the standard error, which is found by dividing the population standard deviation sigma by the square root of the sample size. For a t-test, by contrast, the standard error is found by dividing the sample standard deviation s by the square root of the sample size n. Among other things, this means that we run the risk of underestimating population variability, which increases our sampling error. And this means that t-distributions vary depending on the standard error, unlike z. Let me show you what I mean. So this diagram shows the z-distribution in red, as well as two different t-distributions in blue and green. And this is one important thing to notice right off the bat. There is only a single z-distribution, but there are many t-distributions. The z-distribution remains unchanged because we know our population standard deviation, sigma. The t-distribution, however, varies depending on the degrees of freedom, which for a one-sample t-test is n minus 1. This means that the shape of the t-distribution is directly related to the sample size. The larger the sample size, the more closely the t-distribution resembles the z-distribution. And you can see that here. Notice that as we go from the t-distribution with 10 degrees of freedom in blue to the t-distribution with 20 degrees of freedom, represented in green, the shape changes, becomes more pointed in the middle, and more closely approximates the z-distribution. The closer the t-distribution is to the z-distribution, the less error or variability there is in the distribution. Again, notice that it narrows as the degrees of freedom increase. Now that we've introduced the one-sample t-test, let's walk through an example using the one-sample t-test to test a hypothesis using null hypothesis significance testing. A research question is whether having a growth mindset improves academic performance. A growth mindset essentially means having the belief that knowledge is malleable and that hard work can lead to better performance, and specifically, better academic performance. Previous research has suggested that knowledge is indeed malleable, and that with sufficient time spent learning a new skill, your brain can make the changes necessary to master it. And furthermore, research has suggested that having a growth mindset leads to improved academic performance. In other words, believing that it is possible for you to change and to improve makes it more likely that you will improve. So, now that we've laid out our research question, let's establish our null and alternative hypothesis. Let's say that based on previous research, I have reason to believe that there is directionality. In other words, that growth mindset will specifically improve performance. As such, my alternative hypothesis will be that students who receive growth mindset training will have higher GPAs than the population. So let's say, for the purposes of this little example, that the population I'm comparing to has an average GPA of 3.08. Thus, my alternative hypothesis, represented by H1, is that mu is greater than 3.08. Now, once we've established our alternative hypothesis, our null hypothesis must be the opposite. It must exhaust all other logical possibilities. So our null hypothesis will be that students who receive growth mindset training will have equal or lower GPAs than the population. And again, assuming that the population mean here is 3.08. So we'll represent this as H0, that mu is less than or equal to 3.08. Now that we've established our hypotheses, we'll go ahead and choose an alpha and a critical value. Let's go with an alpha level of 0.05, one-tailed. To pick our critical value, we'll need to look at our table of critical t values. I've posted one as a PDF on GoucherSpace. Go ahead and pull it up now before we continue with this video. So one thing you'll notice about the table of t critical values is that it looks very different than the table of z critical values. The alpha values here are along the top of the table. There are 2 rows in the head for 1 versus 2-tailed tests, and separate rows, sorry, that's an error on the slide, separate rows for degrees of freedom. As I mentioned earlier in this lecture, the shape of the t-distribution depends on the sample size and thus on degrees of freedom, which means that the critical value depends on the alpha that we select, the number of tails, and the sample size. So essentially, to find our critical t value, we begin by determining whether we're running a 1 or 2-tailed test. In this case, it's a 1-tailed test, so we look in the row labeled 1 tail. We read across until we find our alpha level. So we would find the alpha level of 0.05, which, if you can see my cursor, is right here. And once we've identified the proper column, we would then read down the table, which of course is much longer than what you see here, until we find the row corresponding to our degrees of freedom. Let's take a moment to discuss the relationship between sample size and critical values. We'll start by getting a little bit of practice. Go ahead and use the table to find the critical value for a 2-tailed alpha 0.05 test with a sample size of 26. In other words, degrees of freedom 25. And you should find that the answer is plus or minus 2.059. Let's try another one. What is the critical value for a 2-tailed alpha of 0.05 test with a sample size of 101? In other words, degrees of freedom of 100. And the answer is going to be plus or minus 1.984. The reason this is plus or minus, of course, is that these are 2-tailed tests, which means that we actually have 2 critical values, a positive critical value that defines the lower bound of the upper critical region, and a negative value that defines the upper bound of the lower critical region. Another thing to note is that as n approaches infinity, the critical values of the t-distribution approach those of the z-distribution. So, for example, if we increase our sample size here to approach infinity, we'll find that our critical value approaches 1.96, which, of course, is the critical value for a 2-tailed alpha 0.05 z-test. Something to keep in mind here is that smaller samples are associated with higher critical values, which means that we need a larger test statistic to reject the null. In other words, either the difference between the sample mean and the hypothesized population mean must be larger, or the sample variability must be smaller, or both. Overall, the outcome of our hypothesis test depends on the magnitude of the difference, the size of the sample, and the variability of the sample. Let's return to our example and practice calculating the test statistic. So again, we're assuming that our population mean is 3.08. We've selected an alpha level of 0.05, and we've decided to run a 1-tailed test. Let's say we find that our sample mean is 3.18, our sample standard deviation is 0.45, and our sample size is 120. Our first step will be to calculate our degrees of freedom. 120 minus 1 is 119, which, if you look at the table, you'll notice is not listed. So, a very important note. If the degrees of freedom you've calculated is not listed in the t-critical table, you always pick the next lowest, in other words, the more conservative degrees of freedom that is listed in the table. So in this case, the next lowest degrees of freedom that's printed is 100. So that's the degrees of freedom we would select when picking our critical value here. So if you look at the row for degrees of freedom 100, you'll find that our critical value is 1.66. Now we can go ahead and calculate our t-statistic. We'll begin by calculating standard error. Dividing our sample standard deviation, 0.45, by the square root of our sample size, 120, gives us a standard error of 0.04, and then dividing our mean difference, 3.18 minus 3.08, by that standard error gives us a t-score of 2.50. I've posted a stats class video that will walk you through this calculation in much more detail than I've just done here. I highly recommend that you check it out. Now that we've calculated our test statistic, step 4 is to make a decision. We can either compare our p-value to our alpha value, or compare our test statistic to our critical value. In this case, we only have a critical value and test statistic, so that's what we'll use. So our critical value is 1.66, our test statistic is 2.5. What should our decision be? And the answer, of course, is that because our test statistic exceeds our critical value, we reject the null and conclude that students who received growth mindset training had significantly higher GPAs than the student population in general. And remember, our chances of being wrong here are determined by alpha. Because we selected an alpha of 0.05, we accepted a 5% chance that the growth mindset training actually did not increase GPAs. Let's take a look at a graphical representation of alpha value and critical value. So here in blue, we have the distribution of the test statistics if the null is true. The vertical line here represents the mean of standardized differences between sample means and the population mean. In other words, the test statistic. Notice that this distribution is centered at 0, because if the null hypothesis is true, if we draw random samples from our population and calculate the t-scores associated with them, there will be random variation, but that distribution will be centered on 0. And crucially, because we can precisely map the distribution of t-values if the null is true, if we pick a specific alpha value, here an alpha of 0.05, we can precisely define a proportion of the distribution that corresponds to that proportion. In other words, 5% of the area under this blue curve. We can then identify the critical value that sets the boundary of that critical region. In our case, our critical value was 1.66, which means that for our particular t-distribution, a t-distribution corresponding to 100 degrees of freedom, the precise t-value that separates the top 5% of the distribution from the rest is 1.66. Then, once we have our critical t-value, we can see where our test statistic falls in this distribution. Our test statistic, again, is the standardized difference between our sample mean and the population mean. In this case, it was 2.5. Because our test statistic exceeded our t-critical value, we concluded that it would be extremely unlikely to observe that particular test statistic if the null hypothesis were true, and thus we reject the null because the test statistic exceeds the critical value. Furthermore, because our test statistic exceeds the t-critical value corresponding to an alpha of 0.05, we know that the p-value associated with that test statistic, in other words, the probability of observing a test statistic as or more extreme as the one we saw if the null hypothesis were true, must be less than 0.05. We don't know the exact probability, but we do know that that probability, p, must be less than 0.05. So now I'd like to shift gears slightly and talk about effect size. I'll begin by introducing an important distinction. So far we've been talking a lot about significance. Significance occurs when the difference between sample and population means is relatively unlikely to occur due to chance alone. In other words, when systematic variability is greater than unsystematic variability. The question of how unlikely, or how much greater, is determined by our alpha. So even though I haven't used this terminology a ton so far, it's something we'll be talking about a lot as we go straight forward, and you'll hear it a lot in psychology in general. But the big idea is that we refer to an effect as significant, or statistically significant, if we can reject the null hypothesis. So now I'd like to talk about effect size. Effect size refers to how big or meaningful the difference between the sample and the population means actually is. And importantly, effect size is standardized, which allows us to apply the same rules of thumb regardless of what units we're actually using to measure. Importantly, significance and effect size don't always go hand in hand. Effects can be significant, but not large. This means that our findings are unlikely to be due to chance, but the actual effect is small in real-world terms. It is also possible for an effect to be large, but not significant. In other words, even though the effect we observe is large, we can't demonstrate that there is significantly more systematic than unsystematic variability. Let's talk through an example. Suppose growth mindset training is available at UCSB for $200. Is it worth it? As our test showed, the training does significantly improve GPA, but we need to consider effect size. How much does it improve GPA? So let's say the training could reliably improve your GPA by 0.10 points. So this is a tiny effect size, and barely changes your GPA. A 3.3 and a 3.4 are both B+. So paying all of that money for the training might not be worth it. But what if the training could reliably improve your GPA by 0.5 points? This is a larger effect size, and thus a greater change in your GPA. For example, a 3.3 is a B+, but boosting that by 0.5 points to a 3.8 is an A-. So if this were the case, then maybe it would be worthwhile to invest money in this training. Different statistical tests use different measures of effect size. For one-sample t-tests, we use something called Cohen's d. This is the difference between sample and population means in terms of sample standard deviations. So the formula looks like this. Notice that our numerator is the difference between the sample and the population mean, and it's divided by the sample standard deviation. So in our case, our effect size would be equal to 3.18 minus 3.08, our sample and population means respectively, divided by our sample standard deviation of 0.45 to give us a d of 0.22. As I mentioned before, because Cohen's d is standardized, it's in the same units regardless of what your measurement was actually done in, there are some common rules of thumb we can apply to figure out what constitutes a small versus medium versus large effect. So for Cohen's d, values around 0.2 are considered small, values around 0.5 are considered medium, and values around 0.8 are considered large. So again, to wrap it all up, effect size helps us understand the real-world significance of a statistically significant event. Now that we've conducted our test, we'll need to write up our results in APA format. For the analysis we just ran, it'll look like this. I'll go ahead and break down each of these components in turn. There's a lot going on, but it's actually quite formulaic, and once you get used to it, it's fairly straightforward to write based on the analyses that you've run. We begin by clearly stating what type of test we ran, in this case, a one-sample t-test. We next identify our research question and our hypothesis. In other words, we explain why we ran the test that we did. Because it's a one-sample t-test, we're comparing to a population mean, so here we state what that population mean is. We clearly state whether we're running a one- or two-tailed test, and we clearly state the alpha level of the test that we're running. Next, we state the sample mean and standard deviation, and give a clear statement of the outcome of the test. In this case, that students who received the growth mindset training had significantly higher GPAs than the population. Next, we report the results of the t-test itself. We report the degrees of freedom inside the parentheses following the italicized T for t-test. After an equals sign, we state the test statistic that we found. And finally, after a comma, we state the p-value. Next, we present the effect size along with a verbal description. So here we present the d-value and state that this constitutes a small effect. We close with a slightly longer description of our results that explicitly ties them back into our research question. So here we say not just what we found, but what that means for our research question. To close out this lecture, I'd like to talk a little bit about type 1 and type 2 error. So remember from last week that the larger our alpha value is, the lower, in other words, the less extreme, the critical value is, and thus the easier it is for us to reject the null. Additionally, if we run a one-tailed test, the critical value will always be smaller than a two-tailed test at the same alpha, making it easier for us to reject the null if the effect is in the predicted direction. A smaller critical value means that a smaller test statistic is required to reject the null, making it easier to reject the null. And finally, a larger alpha value means that the p-value can be larger while still rejecting the null, and thus makes it easier to reject the null. From this week, recall that the larger the effect size is, the more likely it is that the test statistic will exceed the critical value, and thus makes it easier to reject the null. So, given all this information, should we try to change the alpha, the number of tails, the critical value, and the effect size to make it easier for us to reject the null? And what are the consequences of such changes? So think back to our example and our research question investigating whether growth mindset training improves students' GPAs. So there are two issues here. First, does this training actually improve students' GPA? In other words, is there a true effect of training on GPA? And second, do we reject the null and conclude that this training significantly improves GPA? So there are two possibilities for that first question. In other words, there are two possibilities for the true answer to the research question. First is that the training actually does improve GPA, meaning that the null is false, and thus the null should be rejected. Second is the possibility that the training does not improve GPA, thus the null is true, and the null should not be rejected. Similarly, there are two possibilities for number 2, our decision based on the data we observed. We could either reject the null and conclude that training does improve GPA, or we can fail to reject the null and conclude that training does not improve GPA. These two possibilities for each question yield to a total of 4 outcomes. So in this table that I'm about to show you, each column represents one possibility about the true answer to the question. In the column on the left, there is a true effect, and the null should be rejected. In the column on the right, there's no effect, and the null should not be rejected. Each row in this table represents a decision that we can make based on our data. In the top row, we reject the null, and in the bottom row, we fail to reject the null. So let's begin by imagining a world where there is no effect, and the null should not be rejected. If this is the case, if we reject the null, we've made a type 1 error. If we fail to reject the null, in this case, we've made what is known as a correct rejection. We have correctly concluded that there is no effect. The probability of making a type 1 error, if the null should not be rejected, is represented by alpha, as we've discussed, and thus our probability of a correct rejection is equal to 1 minus alpha. So, to recap, a type 1 error occurs when we fail to reject the null when the effect is not real, and the probability of a type 1 error is given by alpha. Now let's consider a world where there is a true effect and the null should be rejected. Now, if we reject the null, we've made the correct decision. If we fail to reject the null, we've made a type 2 error. A type 2 error occurs when we incorrectly reject the null when the effect is real. The the probability of a type 2 error is given by beta. So there are a couple key things to take away from this table. The probabilities in each column add up to 100%, and crucially, only one column can be true in a given situation. Either we live in a world where there is a true effect, or we live in a world where there is not a true effect. So for example, if there is a true effect, we can make a type 2 error, but we cannot make a type 1 error. Of course, we can never know for certain which world we live in, hence the need for statistics. Let's talk a little bit about factors that influence the chances of type 1 and type 2 errors. So think about what factors are involved in deciding whether to reject or fail to reject the null, since that's what's going to lead to type 1 and type 2 errors. These include the critical value and its associated alpha value, the test statistic and its associated p-value. The test statistic, in turn, is influenced by sample size, the variability of the sample or the population, and the magnitude of the difference between the sample mean and the population mean. So what influences our risk of a type 1 error? The risk of a type 1 error, which again occurs when we reject a null that should not be rejected, is a function of how conservative the test is, in other words, how hard it is to reject the null, and of the alpha. The smaller the alpha, the more conservative the test. Smaller alphas are associated with larger critical values, which means that a larger test statistic is necessary to reject the null. Another factor influencing our risk of type 1 error is the number of tails on our test. Two-tailed tests are more conservative than one-tailed tests with the same alpha level. Using a two-tailed test means we have larger critical values, and thus a larger test statistic is needed to reject the null. So you might ask, if we're concerned about type 1 error, why not have all tests be maximally conservative? As we discussed, using two-tailed tests and smaller alpha values result in larger critical values. Larger critical values require larger test statistics to reject the null. Thus, only extremely large differences will succeed at rejecting the null. So the question becomes, do we want our test to be so conservative that only extremely large test statistics are deemed significant? And this really depends on what question we're asking. If the real-world costs of type 1 errors are high relative to the cost of type 2 errors, then it's a good idea to use a more conservative test. For example, if you're trying to figure out whether a high-cost intervention, for example, surgery, is effective, we want to be very certain that it works, because the costs of mistakenly thinking that the surgery works when it actually doesn't are much higher than the costs of thinking that the surgery doesn't work when it actually does. On the other hand, if there are high costs for type 2 errors relative to type 1 errors, then it might be a good idea to use a less conservative test. For example, if you're considering a low-cost intervention, for example, mindfulness training, that could have a major impact on mental health, it might be worthwhile to run a less conservative test. Because if it turns out you made a type 1 error, you thought that the mindfulness training worked when it actually didn't, you haven't wasted a lot of time or effort in doing the mindfulness training itself, so there's no harm, no foul. Unfortunately, in the real world, there are often high costs to both types of errors. We can see this in the ongoing issue over testing for COVID. As you can imagine, there's a high cost to making someone believe that they have COVID when they actually don't. But there's also a very high cost to making someone think they don't have COVID when they actually do. So we talked about factors influencing the risk of type 1 errors. Now let's talk about factors influencing the risk of type 2 errors. The risk of a type 2 error, failing to reject a null that should be rejected, is a function of alpha. The larger the alpha, the smaller our risk of a type 2 error. Running one-tailed tests versus two-tailed tests, which reduces our risk of type 2 error. But there's a trade-off here. Both of these also increase the risk of type 1 error. We can reduce type 2 error without increasing type 1 error by increasing the size of the test statistic. This can either be done through increased sample size, for example, if we just recruit more participants, or increased effect size. We can use more powerful manipulations or more sensitive measures. Using larger sample sizes leads to smaller standard errors and thus to a larger test statistic, and using a larger effect size produces a larger difference between mean and thus a larger test statistic. We can see this if we look at the formula for our t-test. If we have a larger sample size, and thus a smaller standard error, it reduces the denominator of the t-statistic and thus increases its overall value. On the other hand, if we increase our effect size, we have a larger difference, which means we have a larger numerator, which also increases the value of our test statistic. And this leads us to the concept of statistical power. Power is the probability that we will correctly reject a null that should be rejected, and conclude that an effect exists if it actually does exist. Power and type 2 error are inversely related. When power is increased, type 2 error decreases. Our risk of a type 2 error, as we saw in the table, is represented by beta, and our power is 1 minus beta. This means that, by definition, as our power increases, our risk of type 2 error decreases, and vice versa. The big idea here is that larger sample sizes lead to greater power and to lower risk of type 2 errors. Larger effect sizes also lead to greater power and also lead to lower risk of type 2 error. So, as always, we covered a lot in this lecture, and I want to close with a brief recap of some key points. Z-tests require that we know the population standard deviation, sigma. The t-test, which we introduced in this lecture, allows us to estimate the population standard deviation from the sample standard deviation. Conceptually, one-sample t-tests ask the same question as the z-test. How great is the difference between the sample mean and the predicted population mean, in other words, the systematic variability, relative to the variability of the population as estimated from the sample, in other words, unsystematic variability? The t-statistic gives us a standardized measure of the difference between the sample mean and the predicted population mean, because it divides the difference by the standard error. Crucially, we know how the t-statistic should be distributed if the null is true, in other words, if the sample came from the null population. And that means that if the t-statistic we calculate is sufficiently extreme or unlikely, and again, sufficiently is defined by our alpha level, we reject the null.